There we go. Let me turn this down here. Hi everybody, welcome back to Chem 1. What are we on? 140? It says it on the screen. There it is, 140. I am addicted to seltzer water. This is apparently a thing that happens when you're like in your 30s, I guess, as you start drinking carbonated water. And yeah, I don't know. I don't know why I am so just like, seltzer water is so good, but that's what I have. I drink polar seltzer. This is raspberry lime. Very razzy. Let's see here. So, I've been getting a lot of comments about labs. Since this is week 1, don't worry about the labs. The only thing that you're going to need to do about the first lab is you're going to watch a video and answer a bunch of questions about it. I'm going to introduce that during week 2. When we get to... Gosh, what part of... There's really not a good part of the lectures coming up that's relevant to the lab. We've kind of already talked about it. I guess we can talk about it today. Let me finish chapter 1 real quick, because this last section is basically, hey, what can we not do with science? This is like a philosophy sort of discussion. Oops, I didn't mean to advance that. And then I'll show you... We'll do the lab discussion now. Sure, why not? Because it's going to take 5 minutes. So, in the previous lecture, what we talked about was how we perform science as a civilization and the scientific method and the cyclic approach that we take to collecting data, gathering information, and then matching what we find against our ideas and then shaping our view of reality. What we're going to do now is talk about, like, where does science kind of stop? Like, what's the line between this is science and then this is what we would call pseudoscience? So there are limitations, and those limitations are inherent in the system that we discussed yesterday of like, it's fact-driven, so if we don't have scientific facts, we can't draw a conclusion. And if you do draw a conclusion, then you're going into the realm of pseudoscience. So now, this is where I push the game Paradise Killer, because it has a tagline that is very, very poignant. And the main character says this all the time. You play as... her name is Lady Lovedeyes, and you are running around this crazy, like, 70s style futuristic island, trying to solve a murder mystery. And what she says is that, all the time, she says, the facts and the truth are not one and the same. So, when we have something that uses the word truth, this is something that you derive from a scientific fact. In fact, the word truth is sort of a perception of the reality around you, and your reality may be different than that of other people's based on what truths you adopt. For example, if you are an anti-vaxxer, your truth is that vaccines are bad, and that reality is not the same as someone like, say, me, who believes vaccines are important, and I went and got mine last week. So, don't use the word truth in a misleading way, because it's very easy to do. There is no absolute truth. Truth is very subjective. But the facts that we derive them from, those facts aren't subjective. They are as objective as possible. So we want to use objective stuff to define what's going on. And this, as a result, can become subjective. So be careful about that. In other words, what I'm trying to say here is just because you find a bunch of facts and then you accept, okay, this is what's happening in this system, there is always the potential that exists for you to discover something later and realize, oh shit, everything we know is wrong about this topic. And this has happened a lot in history. So I'm going to go over here. Oops, I didn't capture the right part of this. That's okay. We'll just shove this up in the corner. And what we'll do is we're going to do this. We're going to talk about Galileo. I need like orange for the sun here. So here's the sun. There's my sun. Okay. So here's the sun. And then we've got the Earth, and the Earth should be blue. And for the longest time, people thought that this was how the universe worked. Like this. And everybody believed, oh, the sun goes around the Earth is at the center, everything else goes around the Earth, we are the center of everything in existence. And that's kind of a weird way of thinking, but I mean, whatever, right? So I'm going to hit undo. And we're going to just kind of put a question mark here, because what is the actual orientation of celestial bodies in space? Like, we know that it instead goes like this, right? Now, this wasn't accepted for a long time. In fact, it took Galileo to propose an experiment, and his experiment was, okay, well, I have Venus here. If the sun's rays reflect off of Venus, then we should see only this part of Venus's surface. And everybody knew where Venus was. It was observed in the sky, but only at specific times, like dawn or dusk, you could see it. During the day, it would be obscured because the sun is too bright, and then at night, you'd be looking over in this direction and you would never see it. And so Galileo proposed, well, if we never see Venus at night, then that must mean it's not on this side. And so, doing experimental science, it was determined that, yeah, Venus is actually over here, on this side of the Earth, between us and the sun. But in a different orientation, how we would have expected it to be. So this really shook the foundation of astrology, and not astrology, sorry, astronomy. Astrology is the you are a Pisces, therefore you are grumpy on Thursdays unless you get your coffee and your cat, like that sort of thing. Astronomy is just like, how do celestial objects move? Things are moving apart from each other in space, galaxies rotate around black holes, that sort of thing. So this is an example of, hey, we have accepted something and we've established all of this information around it based on the observations that we had at the time. But then as technology advanced, we learned something new and we had to completely revamp all of our models and everything. So don't take anything that you learn in not just chemistry or physics or anything like that as like verbatim, like this is absolute, like this can never change. I'm going to present the stuff in this class as if it were a truth, because as far as I am aware, everything that we are telling you is either factually accurate, or I am going to present it as a simplification, and then we will clarify it later in 161. So I may oversimplify things, and that isn't with the intent to outright lie to you, but that is the intent to, here's the basics of it. We don't really have enough information to describe it in more detail just yet, but we'll get there. So keep that in mind, that the opportunity for future technology to prove everything wrong is a thing that can happen. And as a little joke I included down here, everything you learn in Chem 140 may be proven wrong the day after you take the final, and then you have to take another class. You'd still get credit for this one, so don't worry. But here's the important part. Let's suppose that this happens, and what do you do with your theory? Once your theory is shown to have a falsehood in it, there are a number of options that you can explore. And so the first one is modification. You can modify a theory however you want to, because a theory is a construct, it's a model, and you can use that to accommodate the new observations, as long as those observations and the theory you're using are grounded in fact. The other thing you can do is say, oh, my theory is no longer valid, that's it, we'll get rid of it, we'll make a new theory, we'll just start over. Not start over, we'll just start working in a different direction. And again, this has happened many, many times in science. So The underlying philosophy that I want you to get out of that is that you can never prove something true. You can only prove things false. Is time a theory? I don't think I can answer that question with what I know about time. Like, I don't know what causes time, or where it originates, or can time go backwards, or is there time before the Big Bang? Like, those are questions beyond my knowledge. I'm not even sure I could give you a law of time, other than that time moves forward in a constructed way that we interpret as like 1 second, 2 seconds, 3 seconds, that sort of thing. That's about the best that I could do. Where did my phone go? I must have put my phone away. I use my phone just to tell me when I need to take a break, but that's okay. I'll just ad-lib it. All right, that's really it for Unit 1. I think the next slide is the hooray slide, so let's see here. Oh, there's one more statement. Now, you are right. If you go too far into philosophy, then it becomes kind of nebulous and weird. However, what we have done as a society is there needs to be some foundation. And so we have blocks where we start defining things. So at some point in philosophy, we set up a definition and we say, okay, this is true because we said so. We're going to do that in science as well, particularly with things like measurement. So, like, what is an inch? Why did we pick this amount? Well, because we said so. This is going to be how our unit of length. What is a meter? It's this long. Why? Because we said so. You could pick any other number, and then we're going to base stuff off of that. All right, I think that's it. There we go. Hooray. All right. I am going to go look for my phone, so give me just a moment, and I'll be right back. Just because I don't want to end class like 30 minutes late. There it is. All right, I have my phone now, so now I know that it's 5:14. So the screen's going to stay blank for a second here, because I got to load the slides for Unit 2. All right, and something should pop up on the screen now. Yeah, there we go. All right, Unit 2 requires a calculator. We're going to do basic math today. We're going to teach you how to do numbers and calculations in science. And a lot of this is actually a new way of thinking for many people who have never taken a science class before. We're going to take all the math that you learned in first grade, second grade, etc., and then show that you've done it wrong. Which is kind of a weird thing to say. Like, huh? I've been adding numbers wrong all my entire life? Well, it's not that you've been adding them wrong. It's that your calculator is doing it wrong, and you're assuming that it's correct. We'll show why that is in this section. Now, in the previous section, we talked about science. Measurements and observations are very important. Measurements are values. They are quantitative assessments of things that we are interested in. So here are some examples of that. Like, if I'm going to weigh out some blue powder for an experiment, it would be nice to know how much I weighed out in case that's relevant. Maybe a reaction requires 5 grams, and if I don't put enough in, nothing happens. So having that number available is crucial. How long is the test tube? Can I put this object in there, or if I do that, will the water that is also in there get overflowed? Like, how much liquid does this beaker hold? These are all number-related things that I could measure and that I would want to know. So when you make a measurement of something, you are determining some sort of quantity. Now, that quantity will have 2 parts to it. The first part is the numerical value, And then the second part is the unit. We're going to talk about the units on the next page here. Now, importantly, whenever you make a measurement, you need to use some sort of tool. Human beings are good at perceiving their surroundings in terms of qualitative description. So I could say that, oh, the color I used on this screen is blue. Or I could say that I am roughly 110 kilograms in weight, or something like that. But what I can't tell you is that to any level of precision. So, like, I'm holding my can of water, and I don't know how much this weighs. I would guess, like, 300 grams. But could I get down to 0.1? No, I'd have to use a balance for that, because people aren't capable of doing that without either very, very, very specific training or just being psychic, which is not a real thing. So we have the number, but we need to append something to the number to give it a meaning. For example, if I show you this sign on the highway, to all of us, we know what this means. You can't go faster than 65 on the little speedometer on your car or motorcycle or whatever, or else you risk getting a ticket or something like that. But in science, this sign as written doesn't mean anything. 65 what? Sure, officer, I was going 65 feet per second. That's like 120 miles an hour, by the way. That won't hold up in court, obviously, but in terms of science, this number isn't really meaningful. We need to append something to it to convey this information to somebody else. This can get confusing if you go across the border to Canada and you aren't aware that their speed limit is in kilometers an hour, and you start driving down the highway going 100 on your speedometer, because their speed limit is about 100 kilometers an hour, which is roughly 60-ish miles per hour. So not having those units there can be ambiguous. And in science, the last thing you want to do, if you want your measurements and your experiments to be reproducible, is to be ambiguous. So a measurement will always contain two parts. It has the number, but it also has the units. Now, in an in-person class, I would require every measurement that you write down to contain both the number, which is the answer that you get, and then the units that you append to the end. It's important to have both parts. But because this is an online class and you're going to be entering all of your answers for calculations and stuff into Canvas and worksheets, when you enter the units will depend. For stuff on Canvas, I will try and give you directions that will say just enter the number. Don't enter the units. I will tell you the units that you want your answer to be in, and then you will just tell me the number and put that in the answer field. Because the formula questions that I use expect numbers as their answers, and if you tried to type in 65 MI/HR and then hit enter, it will say this is not a number. And that's just sort of a constraint that I have to work around. So in Canvas, you definitely want to use your number unless explicitly told otherwise. In a lab report or something like that, it depends on the context of where you're putting your answer. If I ask you a question and there's a giant blank answer field, you definitely want to include the units in it. So, like if I say, what is the length of this object? If you wrote 32 in the box, I would mark it incorrect. If you wrote 32 centimeters, I would mark that as correct. Excuse me. If you have a number in, say, a table, then there's two ways to go about doing that. And so let's go back here real quick. Photoshop. I need to. Oops, hold on. Sometimes when I maximize Photoshop, it doesn't quite work. There we go. So let's suppose that you have a table that looks like this. And in this row, I want you to write the mass of stuff. So if I ask you to write the mass of an object, you would write its number and then the unit after it. And so that would be good. Now, another way that you can do this is you can write the units next to the index or the label on the table. And then in that case, you don't need to write the units anymore because you've already done that. What is the mass in grams? Well, it's 4.25. Okay, so either you need to indicate your unit in the table or after each value. If you do both, it's redundant. But it's not, I would not interpret that as confusing. If they didn't match, that would be confusing. That would be a problem. But if there are no units anywhere in your table, then that's an issue. Okay, and that would be grounds for marking an answer wrong. So when you are doing your reports on those worksheets, on the Google Sheets that I've uploaded, and anything starts asking for numbers, check to see where the units are, because sometimes I put the units in the table, sometimes I don't, and I'm expecting you to provide the units yourself. It depends on the context of the question and the situation. So be mindful for that, basically. All right. Excuse me. Whenever you are making measurements with tools, there's going to be some degree of error. But what times are applicable to measurements where there is no possibility for error to exist? And it turns out that there are very, very few times where there will be no error in a measurement or calculation. And those times come up with these two situations. I say that it's true, and by I mean we as a society or somebody important or whatever, or we count something. So if I asked you, for example, how many eggs are in the carton in the fridge, and you go, oh, okay, well, I have 18 eggs because I just bought one carton. There's not going to be any error associated with this. There's not, like, this doesn't make sense. Could you have 17.9 eggs? No, that doesn't make any sense, right? Because eggs are discrete individual units, and I'm counting them. So if you are counting something, there will be no error with it. There are exactly 18 eggs in here. Are all the eggs the same size? No, but we aren't counting in terms of like mass or weight or volume or whatever. We're only just counting individual units. So counted things are exact. The other things that are exact are definitions. If there are 12 inches in a foot, there are exactly 12 because we said so. I took whatever a foot is and I subdivided it into 12. That didn't quite work. Ow, son of a bitch. Whatever. I broke it into 12 pieces. You get the idea. And each of those pieces are equivalent, and I have set up all of my measurements such that this is true, because we have just arbitrarily decided it. These are the only two times that measurements will be exact. Any other measurement that is made with any other tool that does not rely on counting will be inexact. So as an example, if I go over here to this screen, and I guess I could show you this screen here. Yeah, here we go. So this is the screen that I see when I have the lecture going on live stream. So now you can all see what's going on behind the scenes. So I can see how many people are watching. Right now there are 11 people watching. Somebody hit like. That's cool. But this number right here that you can see, this is an exact number. The system is counting the number of people that are connected right now to this stream, and there's no error associated with that to the 10th place. It doesn't make sense that 10.8 people would be watching, right? Oh, yeah, how high can we get the number, you guys? And then everyone's going to hit dislike, and I'm going to be kicked off the channel, right? So things that are counted are exact. There's no error. I can assume that there are exactly 11 people watching the stream, and that 4 of you have hit the like button. Like and subscribe, everybody. If I counted the number of cans of polar seltzer in the fridge, that would be an exact number. But if I were to ask you, what's the we didn't lose 9 people. There are 24 people in this class, but I don't expect that everybody will watch these lectures live. Like, that is not a realistic expectation. What if I asked you what's the volume of soda in all of the cans of polar seltzer? Well, that I could not tell you by doing a calculation, because even if I read the side of the can where it says 355 milliliters, is it safe to assume that every can has 355 milliliters in there? Some might have more or less. It's hard to say. These are some more examples of exact definitions that we have just chosen. So some of these are weird. For instance, the speed of light, we have defined that as how far, or sorry, not the speed of light. Sorry, 1 second, we have defined that as how far it takes light to travel this many meters. 299792458. For a cesium atom will have an electron that bounces up and down 9 million something times. This number got carriage returned, unfortunately. Like, we've just chosen these definitions for 1 second. And the second one is pretty useful because we can actually count this number of transitions and define that as a second. So we have a physical basis for time. And it's interesting that people were talking about time, because I knew we were going to define time later on, but I didn't really want to give too much away about it. Time is based off of the cesium-133, which is interesting. But that doesn't tell us what time is. It just gives us a way to track it. All right, let's talk about some inexact numbers. I'm going to put this on the screen here. Based on what you see, what's the volume of this of the water contained in this tube? And you can go ahead and type your answer in the chat if you'd like. Just type what you think it is based on what you see. And the only information I can really tell you, without giving it away, I mean, obviously it's going to be one of these numbers, is this number right here is an 8. Now, you'll notice that people are actually entering in different numbers, right? Not everybody is getting the same number. And in fact, I think I've misled you, because I just realized that I may have counted the marks wrong when I wrote this slide here. Probably more like 8.1 something. We're going to talk about how to use this tool to measure it in just a second. But this brings up the concept of something that is inexact. So if I wrote down a number for this tube, so let's just write, I'm going to just write 8.16 here. These actually should be ones now that I realize it. I'm going to put the units down here for a specific reason, and then I'm going to get a different color. So let's suppose that was the volume that I recorded. But does that mean that this is true? Are the zeros that I put in black accurate? Do we know that those are a thing? Is it 8.16000000? That seems extremely unlikely, right? That it would fall on all those zeros. So because we can't determine these all just become question marks, and so we don't report them. We would need an infinitely more precise tool to get all of those extra digits, and the ticks can go further and further and further and further and further and further down, right? And then, yeah, you have questions about the accuracy of the tube itself. So, like, this was made by some sort of machine painting on lines. Is the machine trustworthy? Has it been calibrated recently? Like, these are all questions that we can ask. And so the end conclusion that we draw is that when we get a number out of a tool by doing a measurement, because I can't count it, I have to measure it, I'm going to get an inexact number. Somewhere along the way, my result is going to be subject to some level of interpretation. Here, the interpretation is us. Our eyes are doing the interpretation. For a machine, the machine is trying to take the average, which is interpreting, like, oh, here's one result before the mark and one result after it. I'm going to take the average and report that as the answer. So if you have to measure it because you can't count it, it's impossible to count, it's inexact. If you can count something reasonably, it's exact. Now, if you're working with something that has a very small scale, then you need to have very small marks. Now, with a graduated cylinder, that's not possible. We can't measure microliters using this graduated cylinder. The marks would be on top of each other, practically. So we need to devise a different sort of tool or a different sort of system of measurement entirely. And that's where, yeah, you start getting into things like digital instruments, like calipers. Calipers are very, very, very fine tools that are used to measure. And when that starts to fail, you use things like lasers, which measure the distance and the time it takes for light to be emitted and then reflected back to a sensor. That sort of thing. The year is not 2020 anymore for this example, but what I want you to do is look at these numbers and then report in the chat which ones are exact numbers and which ones are inexact numbers. I've tried to disguise them in such a way that it's a little ambiguous, but there is a definite correct answer to each of these, okay? Think about which of these can be counted, and those are exact, and which of them should not be counted because you could reasonably measure them with a tool or something, and those must be inexact. So report your answers in the chat, and we'll go over the answers together in just a moment. Now, this is a good discussion that people are having in the chat, so keep talking about it. I will give you my interpretation. But again, some of this is subject to interpretation. In fact, that first one relies on how much do you know about time and how we define it, and then, like, what is, like, a day? What is a year? What does that all mean? And I will tell you the correct answer when we go over the problems. All right, one more minute and we'll go over the answers. All right, let's start at the bottom because that's the easy one, right? How do we count years? Just 1, 2, 3, 4, 5 until we get to this awful year, right? So this is definitely exact. Because the number we assign to a calendar year is pretty arbitrary, right? We just picked some point in time and measured from there. Well, not measured from there, but counted from there. We said, okay, this is year 1. Appropriately, Easter was like 2 days ago. So we called, okay, this is the day that we're going to call year 1. And then from here on forth, every time we pass a year, we will count it. So the year that we are in is counted. Let's just work our way up from there. How do I get the mass of something? How would I weigh my Jeep? What would I have to drive it onto? Can I look at it and go, oh, it's 2009 kilograms? Yeah, I had to put it on a scale or something, right? So if I drove it onto a balance, the balance would tell me its mass against some standard reference, right? And since they are using a tool for that, the weight could actually be something like this, which would just round up to 2009. Landing exactly on a kilogram would be really, 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 really difficult because even like a paper clip would push me off of exactly 2,000 kilograms, yeah? So since this is something that we would measure using a scale, this becomes inexact. I can't count the weight of my Jeep. I guess I'll just leave scale in there. How about the number of steps that I walk to the store? Now, this is a really large number. Could I count to 4,096? I could if I had enough concentration. So that's pretty feasible. I could count this. But here's a better question. Is it possible to walk half a step? So I put my one foot in front of the other, but I only take half a step. Can I do that? That's not a thing you can do, right? So that means that these are incremental discrete things and must be exact. Now, if you use an instrument to count the steps for you, such as a, what is it, pedometer? I use my 3DS to count my steps. Because it's really good at doing that. But what the 3DS will not do is it will not say you walked 4,094.7 steps today. It will round that off to every step that I take. Now, are all steps the same? No, they're all different, right? But I'm not asking you for the distance I travel. I'm just asking you for you how many steps that I take. And that number is exact. I could report that. How about a glass of water? If I measure out 533 milliliters into a glass of water, How would I determine that it had 533 milliliters? Well, I'd take the glass, I'd pour its contents somewhere. Where would I pour it? In the sink, in the toilet, out on the lawn, that sort of thing. Now, with the steps being subjective, it is a subjective unit of measurement if you're considering it in terms of distance, but we're not talking about distance here. I'm just talking about how many steps did you take? What number would you report? I would report 4,096. You might report 4,250 if your legs are shorter, or you might say whatever. But the point is, you could count the number of steps that you took. Now, for water, I would have to pour this into like some sort of graduated cylinder, or maybe a beaker, or something like that. And that beaker or tool would have marks on the side of it that would allow us to get this number. And since we're using a tool, this would be inexact. Now, a dispenser would work too, but we'd have to calibrate the dispenser, and we'd have to do that in the same way with these. All right. If I'm driving a distance, how is distance measured? This is actually different from steps, right? Now, if distance was related to the number of times your wheel rotated, that would get you closer, but you can actually rotate a wheel partially, right? I could drive forward such that my wheel rotates only halfway. So what's the answer here? Yeah, the way that your odometer works is it measures the number of rotations of your wheel and plots that against an incrementer. Every time it goes around this many times, I increment the display, the digital display on your car by 0.1. Now, because that is a measured quantity that we're using a tool to do that, this is inexact. Another way to think about that is it possible I could have driven 12.999 miles instead? Yeah, maybe I stopped a little bit slightly earlier in the parking spot than I normally would. So I couldn't drive exactly 13 miles. Now, the last question, which ironically I put first, I always think that this is pretty straightforward, but then a lot of people talk about this, and more I think, oh, maybe this isn't such an obvious answer. Now, if we use this as the calendar construct, as in this is one box on my calendar, then what ends up happening is that, okay, this is defined by this. And then we would say that that's exact. Because we have just chosen, okay, to advance the next day, 24 hours must pass. However, you could also base this off of what's called the solar day, which is how much time does it take the Earth to rotate around in a circle? Well, if the Earth was stationary, it would take one period to rotate completely, but the Earth is moving, right? So it will rotate around completely, and then it has to rotate just a little bit more so that it's pointed at the sun in the correct orientation that it was before. And that gets a little bit weird, right? Especially since the Earth is tilted and other factors and phenomenon come into play when trying to measure that. And I've used the word measure there, so you already know that, oh, okay, well, maybe that would be inexact. There's actually like 24.00000 whatever. We go over a little bit, and so that we have to make up for that day or something like that. And that's actually where leap year comes in, is when we go around the sun, it takes 365 days plus 0.25. And that 0.25 times 4 is why we have every 4 years we have a leap day that we put in February 29th. Now, you're getting back to the construct question, where we have chosen something to measure a second, which is what hours are based off of, which is what days are based off of. And that would lead us to this conclusion right here, yeah? So if hours are based off of the cesium measurement, and that's something that's defined, then yeah, this would be counted. So that's where we're going. We're going at solar years, which is, oh, we measure a year as how long it takes the Earth to go around the sun, versus, oh, we measure a year as this many seconds pass. One of those is defined, but the other one is measured. So the whole point of me putting that one there, and I really should just move this to the bottom of the list so we can have this conversation at the end, is to get you to think about, oh, which things are constructs? Which are things that humans have chosen? And then what are we applying those things against objects that exist in reality? Like, I can define a kilometer as something, but no object in reality will be exactly a kilometer. And that's okay if you make mistakes here. The point is to see these and go, oh, okay, I sort of see where he's coming from. And then you'll get more of these as we go on, and you'll be able to answer the question. I picked particularly mean examples here. The takeaway that you want, really, is that if it's something that is counted because it's a system that we have set up in place, that's exact. So like 12 inches in a foot, that's exact. 1,000 meters in a kilometer, that's exact. We have chosen those things to be true. If I use a physical entity and then try and adapt this model to it, then it's going to be inexact. So like a distance versus an actual trip that I can take. I can't ever land on exactly the distance I've defined, because I will always be off by even like the width of an atom in one direction or another. It's impossible to land exactly on what I define. All right. If you have other questions, let me know, because we are going to veer into the realm of the strange, I guess we'll call it. Let me see how long precision and accuracy is. I actually want to start this next section off of the break, or after the break. So, for miles, my car is not driving exactly 13 miles, because the miles themselves are defined as a certain number of feet and inches. But if I make a reasonable trip from my parking space here to the parking space at Everett, would I land exactly on that number? Do you think it's possible for me to land exactly on the number of miles, which would be the number of feet, which would be the number of inches, down to the last inch? The odds of that are unlikely. And what's more likely is that when we get to this next section down here for sig figs, these two right here. Oh, you can't see that because I'm writing in black. That's also black. Oh my goodness. Pick a color. There we go. These two things right here. Yeah, the error is in the car. What you're going to see is that if I'm measuring with a specific tool, and I get something like this, but my tool is only good for measuring to the ones place, I would round that to this. All right, but we're going to come back to that after the break here. So let's put this on the screen. I don't have my timer out, so I got to get that real quick. So in about 10 minutes, we will reconvene. We'll get started on talking about what it means to be precise versus accurate, how we measure and interpret error, and then we'll do a more thorough discussion of how we do math and stuff to round out the lecture. So I'm going to start the timer. I'm going to turn on the music, and I will see you in just a little bit. Alright, we're back. Let me turn this down here. Alright, so before we actually go on to the next section, I do want to talk about the lab a little bit. So I need to put this on the screen. And then I have to capture... That's live split. That's not what I want. Yeah, that's what I want. Yeah, there we go. Boop. Okay. So I'm on Canvas. And what I did was I went into the modules. And I clicked on Lab Worksheet number 1. So I'm going to start here. Let's talk a little bit about Lab Worksheet number 1. And actually what I'm going to do is, instead of having it on the screen like this, let me open the actual PDF file here. And then I'll just capture that instead. So, boop, there we go. All right, so lab number 1 is about observations. We'll just cover up B. That's fine. Like, you could use your eyes to tell the difference between this rat and this cat, right? One is adorable, and one is the fattest rat ever. Like, you could tell the difference between those two very easily using your senses. But with chemicals, it's a little bit more difficult. One of these is sugar, and the other is methamphetamine. Which is which? And are you sure? Because I've chosen pictures that might surprise you. And now that you've said that, you've probably switched your guess, and am I just trying to trick you? It's hard to say when you're just using your vision. I want 100. There we go. To do that sort of thing. So what we need to do is we need to do other sorts of tests in the laboratory to produce other phenomenon that we can then use our senses for. Now, an example that I give here is that you can do a test with something called Simon's reagent, and what it does is it will react with specific molecules that have specific groups on it. Specifically, a secondary amine, which methamphetamine has. So when you expose Simon's reagent to methamphetamine, you get blue. When you expose sugar to Simon's reagent, nothing happens. You get no color change at all. So this is a good test. We can just put the unknown white crystal into the solution, shake the bottle, and if it turns blue, hey, it was meth. From what I have been told, you can also taste the difference. I don't know that for sure. I have never encountered meth. I actually know how to make it because I'm a chemist. You'll learn that in organic chemistry. Take 262 that will teach you how to make meth. I mean, doesn't the picture on the right look shady? But when you crystallize stuff, and you're actually going to crystallize things, well, I guess you would if you were in this class. You crystallize a lot of stuff, and it comes out as needles like this. You get the square crystals from some other type of process. I think this might be more just like, once you put this stuff on the right into like a container and you like let it tumble around, then it becomes more square-like. But I don't know that for sure. Anyway, the purpose is that we're going to use other methods to remove all the obscurity from this. And the way that we do that is I'm going to give you a bunch of chemicals. Here are the chemicals I'm going to give you. I'm going to give you three unknowns. One is sodium something, and the other two are something nitrate. These three chemicals are, each of them is one of these things. You'll notice there's a bunch of sodiums. So unknown number 1 has to be one of these 5 things. And then unknowns number 2 and 3 have to be one of these 5 things. And what we're going to do is we're going to mix all the possible combinations together. So this is just an example of some other experiment that we'll do, that I'm using for the pre-lab, where you're going to look at this test and say, okay, I mixed A with 1, and I got milky yellow. I mixed A with 2, and I got red. I mixed A with 3, and I got colorless. Now, if I mix 2 different things together and I get 2 different results, like right here, milky yellow and colorless, A and B can't be the same thing because I got a different result when mixed with 1. But if I mix B and C both with 1, and they're both colorless, maybe B and C are the same thing. So I'd have to test a different thing. So I'll use 2. Oh, they're both red. Maybe they're still the same thing. I'll try 3. Oh, they're still the yellow. Maybe it's the same thing. So I'll try 4. Oh, no, I have a difference. So B and C must be unique. So that's where we're going with this, is we're going to try all the different possible combinations and make a giant table. And that giant table, you're going to see on this screen right here. There we go. So here's the giant table. You're going to record all of the observations of what you see for each of the chemicals before you mix them. So this would be barium nitrate, this would be copper 2 nitrate, and so on and so forth. And then up here, this would be sodium hydroxide, sodium phosphate, sodium chromate, etc. This actually goes pretty far over, so just make sure you go all the way over. And then what you're going to do is I'm going to show you a video of me mixing sodium hydroxide with barium nitrate, and you'll record what you observe in the video. You're going to do that for every other combination. They're going to be shown 5 at a time because I take all the nitrates and then I add sodium hydroxide to them. Then I reset and I do that with sodium phosphate. And so on and so forth. Now, there is a video. I produced the video, which is why the camera quality is not great, unfortunately. So if we go to this and I copy this link and I paste it into here, I'll just open a new tab here. We get my really stupid video that I made. We don't need the rest of this on the side here. And it has music because I'm a dork. So I made this video. I'm not going to play the whole video, but your job is to figure out what these things are. This is me. By the time I got around to actually making the video, I was very sweaty. So my hair looks really awful. So we'll mix all the things together, and you can see that I do this. We'll just fast forward a little bit here. And it looks kind of like this. And we'll just put some stuff in there. Hold on, real quick. There we go. So you're going to get to a point where it says pause the video. You're going to do this each time. Now, I realize that, unfortunately, on my camera, I didn't realize this until I was done and I got home. My camera that I had was this little teeny tiny viewfinder that is smaller than my smartphone. And when I looked through it, because you could see that I put it up there and then I walk away because I move my hand, I am going to check the video just to see that I can see it. And it looked fine, but it was really small. And then when I looked at the video after 3 hours of recording and I had already gone home and sent myself the files, it looks really blurry. That's not your fault. Do the best that you can. So what I'm going to ask you about on this lab, when you're looking at these observations, I'm going to ask you to look for the following 4 properties. And that's discussed in the lab right here. So the first one is color. What color do you see? Write down the color the best that you can. Like, is it blue, orange, pink, colorless, whatever you want to. Don't use the word clear. Clear is not a color. That's actually opacity. We'll talk about that in a second. What I want you to do is try and describe the color in a way that you'll remember it if you saw it again. Because I'm going to assume that you're going to do this one at a time and just fill in the table as you go. Pause the video, write down your observations. So in the first line in the worksheet, here it is right here, you're going to type the color that you saw. So maybe you would type in pale orange tint or something like that. In the second box, what you're going to type in is the opacity. Opacity is just, can you see through it or not? And that is going to be a little bit difficult to tell with the video, but here's my advice. Notice how you can see the light. Oops, you can't see my cursor. Notice how you can see the light reflecting off of the paper in the background. If you can see the light going through it, the solution is transparent enough to allow light to go through. Notice, though, that I can't see the light on this one, so this would be opaque. Okay? Use that as your guide. Can you see the light reflecting off of the paper in the background for opacity? The third one that I want you to look up is texture. Texture is like, can you describe this in such a way that helps me understand what's going on? Avoid the word liquid, because all of these are liquids, right? Liquid doesn't tell me anything. Instead, I want you to tell me, can you see a precipitate? Is there a solid in there? And you kind of can, right? So in this blue solution, it looks like something settled to the bottom here, whereas in this one or this one, it doesn't look like anything has appeared at all. So just describe it as best as you can. And yes, I do understand that it is blurry. And then in the last column, what I want you to describe is anything noteworthy that this solution makes you think of. This could be something like applesauce or melted ice cream or even like baby vomit or cat diarrhea. Like whatever something looks like, and like you look at that and like, oh, that is definitely X. Write down whatever X is so that you have something in mind just in case you see it again at the end when I test the unknowns. Okay? Because at the end I will say, here's the unknown, what is it? And I will show you the mixtures, and the mixtures are going to match up with something you saw in the video to some degree. I will give you a warning that one of the unknowns is slightly ambiguous. I chose the unknowns before I did the experiment, and then I did the experiment, and I got to the end, and I was like, shit, two of these look the same. I will accept either answer, but I do want you to justify your answer by citing observations. Now, if you look extremely carefully, you can tell the difference for the unknown that is ambiguous. But I will not grade only that one. I will also grade the one that it looks very similar to. And on your lab, when I grade it, I will write okay, just to say, oh, that wasn't what it was, but that was the really close one. That's acceptable. Okay, that's the experiment. You're going to be filling out the data table. Let me get rid of this here, and then we'll go back over to this one. You're going to fill out the data table, and then over here you're going to answer some questions about it. Type the name of what these were, and then explain your thought process. And when you're explaining, I do want you to cite experiments. This didn't actually... Oops, I'm on the wrong screen here. There we go. All right. How do you get this documentation and use it? So I'm going to walk you through the process here. So if you go to the Modules tab, there's this button that says Lab Primer. And you can follow this document and go through it and figure out what's going on. But here's the gist of it. So if you open this in a new sheet, so if you click up here where it says Google Sheet for Lab Worksheet number 1, what this does is it opens it in a new window. And mine's kind of scrolled off the top because I don't have enough space here, and I need to actually get this part of it. There we go. So the first thing you need to do, this is the blank document. You can't type into this. That's not going to work. What you need to do is first make a copy. And it will tell you, what do you want to call this document? You can call it whatever you want to. It's going to save it to your drive, which is what you want. Don't check these boxes. And then a new version of it will open that will look exactly the same eventually. It will open. There we go. All right. This is now your copy. You can enter whatever it is that you want into this and enter all the answers. Down at the bottom, which you can't see because it's scrolled off the screen. Oops, I need to make this bigger. There we go. Down at the bottom here are tabs. These are different parts of the worksheet. So the first tab is pre-experiment. I'm going to ask you some questions about the idea of the experiment, which are in the documentation over here. And so these are these questions. So you'll need both of these documents to answer stuff, because I don't put this graph into this because I don't have enough space for it. Student drive is totally fine. Yeah, wherever it defaults to, that's fine. as long as you have a copy that you can then input stuff into. So once you've answered those questions, then go to the next tab. Follow the directions. You're going to fill out this table. There's also a table for your unknowns down here, just in case I didn't show that. And then once you have all of that, you then go to the analysis questions, and then you answer those questions. When you are done, what you do is you go File, Download, Microsoft Excel, XLSX. If you choose any other option, Canvas will not let you upload it because I have set it to only accept this file. So you click on this, you save it to your computer, and then when you go to the labs for the assignments, lab worksheet number 1, you go over here. Actually, let me hit student view real quick. So this is now what you see. It's currently not available, but when it is available, there will be a button here that says upload a file. You choose that file and hit a button, and it will be submitted. And then when I grade it, this button will get checked over here. Okay? Oh, you can't see that because, again, too big. Sorry, there we go. That's the gist of it. If you have any questions, you can let me know in Discord or email. I'm happy to walk you through the steps, but that's what you need to do for all of the labs in this quarter. Save your own, make your own copy to your drive, save the XLSX file once you are done, and then upload it to Canvas. Real important, don't open the file to check it for formatting or issues like that before you upload it. Do everything in Google Docs before you download, and then upload the file without uploading it. Just because if you upload it and then accidentally save, it might save formatting stuff, which will break. The last thing that I will mention is that when you upload something to Canvas, Canvas is not capable of interpreting Excel sheets. So it will try and show you a preview, and the preview will look broken. Don't worry, it will be okay when I get the file, because when I download it, I am opening it with something that does interpret Excel sheets correctly, which is my Excel program. Okay? You have to follow these directions in this order, so make sure that you are following that lab documentation wherever it is. Oops, I got to get out of student view. Yeah, there you go. Now you can see the upload file. Where was I? So make sure that you are following the directions in this lab primer. Because if you stray from them and I get a file that is invalid, you're going to get an email from me that says, hey, the file is invalid. You need to send me the correct file or I can't give you a score. Okay? That's the lab. Let me know if you have any questions on that. And let me just minimize a bunch of things real quick. All right, so let's get back to the lecture here. So for this section, what we're going to do is we're going to talk about precision, accuracy, and error in measurements. What does it mean to get a bunch of numbers and then look at them all together? All right, so the first thing that we're going to do is talk about our strategy. We can't take one measurement and then assume that, oh, we did it right. Mostly because this is an introductory class, and the opportunity for you to make a mistake in the procedure is high. Now, that's being said as if I was teaching this class in person, and you had all the apparatus in front of you, and you were doing all of the steps one after the other without any errors. Now, the odds of your error persisting go down considerably if you do multiple trials over and over and then take the average. Because what you can do is you can look at all your data points and say, oh, the first 4 are good, but the 5th one is no good because it's way too high. Maybe I did something wrong there. And so you can just omit it as long as you can justify it. But one data point by itself you couldn't tell, and 2 data points by themselves, if they were very different, you wouldn't know which one is valid. So we generally take 3 or more trials in chemistry to get decent results. Now, there's all sorts of places that error can show up, and what we're going to do for this discussion is try and isolate some of those places where that can show up. So let's look at an example here. I have a graduated cylinder, and I asked 4 people to write down what they thought the measurement of this number of milliliters of liquid was in the container. And they reported to me these numbers. And what I want you to do is, even though you've seen these numbers, what I want you to do is try and write down what the correct volume is that you think it would be in the chat. And we're going to accept that as the true answer, whatever it is you write down. So go ahead and type that in the chat right now. Okay, I see a bunch of 555.5s. Now we're getting more numbers in. All right, we're going to assume that 555.5 is the correct answer here. Now, let's look at the students' measurements, and we're going to do two comparisons for these numbers that they have reported. So, we'll record that as the true value. So the first thing we want to consider is how close is the average, I can't spell, average. How close is the average to the true value? Oh, if you have a blurry, if your resolution is blurry, down over here on the window is a gear icon. Click on the gear icon, and then where it says resolution, or change it to HD or 1080p, and that should fix it. The second thing that we want to consider is how close are the measurements to each other. All right. So this first topic that we have right here, we're going to call accuracy. If the average and the true value are close to one another, then we consider the measurements to be accurate. For this second one, we're going to call this precision. If the measurements are relatively close to each other, that is, they only really differ in the last digit, maybe the last two, very slightly, then we'll say that the measurements are precise. Now, these are separate entities. You can be accurate but not precise. You can also be precise but not accurate. We're going to look at all sorts of different examples here when I show you a picture of targets at a firing range. What we would say is that, okay, these numbers are relatively close to each other. They only really differ in the last digit. So these measurements are precise. And then somebody said that the average for these measurements was like something like this. That's pretty close to the true value, right? So we would say that this is also accurate. So these measurements were made properly. Now let's look at a different set of measurements here. So those are just definitions that I just cited here. Let's look at these. What's the average for these measurements? And then if you took that average and you plotted it on the graduated cylinder, where would you end up? You'd end up where the red line is, yeah? Oops, that's the worst arrow I've ever drawn. That was supposed to be the letter I, but my pen didn't leave the tablet here. So there's a pretty big difference here. Like, it's noticeable. Something happened in this measurement. So now my question would be, is this precise? And or is it accurate? So let's talk about precision. Are the values close to each other? I would say so. They all differ by just the last digit, right? This would round up to 4, so these are really only off by 0.1 of each other. So this set of data is precise, but because there's a significant deviation from the correct answer, what that means is that these students that made this measurement all committed the same error in getting their result. So maybe they looked at their measurement from down here, and that was how they did it. And so they just got the wrong number because this was maybe elevated or something above everyone's head. So we would say, oh, okay, well, there's a significant difference between the correct answer and the wrong or in the true answer. I'm sorry, their data versus the correct answer. Now, I don't really assign a % threshold to this. This is sort of an eyeball thing. You should be able to tell, oh, those numbers are very close to each other. They're precise. Oh, those numbers are not very close to each other. They are not precise. So you'll know that when you see that because the numbers will be quite far off. Depending on your application, different thresholds are used. For accuracy, for the problems I give you, you will be significantly far from the correct answer. Like, if the average was this, and the true value was this, that's pretty far off, right? So this would not be accurate. And for precision, look in the last digit to see if the deviation is in the last digit. And if the number is big enough, maybe the last two. So this one for sure, and then this one possibly. Don't get fooled if you see a 3 there compared to all those 4s and think, oh, that one's really far away, because the difference between 3.9 and 4.0 is actually just 0.1. So be aware of how numbers work and that things carry over and so on and so forth. All right, let's look at some other visual examples here. I'm going to come back to this error in just a second. I just want to show you this page real quick. These are 4 examples of marksmen shooting at a target with varying degrees of precision and accuracy. I'm going to start down here at the bottom. If you are accurate, you are close to the true value, which we would say is the center of all these bullseyes right here. Oops. So the red mark is the true value for the target. If you take the average result should be right in the bullseye. And for this one it is. And up here, it actually is too. Like, it's right there, right? Now, precision is going to be how close things are to each other. So in this example, these are all very precise, but there is some deviation from the center. So what would cause this to happen? For example, this right here, this is my level 20 marksman firing at a target with his revolver because he has a dexterity score of 26 or something. He's a very accomplished orc marksman. He hits the bullseye every time. This would be somebody who knows what they're doing, but their sight is wrong, or the scope is poorly aligned. And so this would be some sort of error that has been ingrained in the device that they were using. So it's being used improperly, but there's still a degree of skill involved. So one thing might have messed up the measurement, we'll say here. Up here, we have more in the realm of chance. So right here, this person got what we call the Statisticians Bullseye, which is the statistician goes out and hunts elk or deer or something. He shoots 10 feet to the right of the deer and 10 feet to the left of the deer, and the average shot kills the deer. That doesn't actually happen, obviously. And that's in a laboratory, that's no good. You don't want to have your results average out to the correct answer because that's just chance. This one over here, this is a novice. This is somebody who it's their first time at the range. They've never held the weapon before. They aren't familiar with it. They aren't sure where to aim, and so they're just sort of hoping for the best. And, I mean, if you hit the target 4 times out of 4 and it's your first time at the range, like, I think that you're doing a good job. This being said by somebody who has held a revolver and fired exactly 1 round at a target, hit the bullseye exactly, and then said, "That's it. I don't need to shoot anymore. I have demonstrated perfection." That is a true story. I have shot a weapon 1 time. It was a revolver. I hit the bullseye, and I was like, "That's it. I'm done. I've mastered shooting. That's all I need to do." Obviously, that's not a true statement that I've mastered it, but I did do archery in high school, though, and I was actually really good at archery for some reason. Like, I'm not good at physical sports. Like, I like tennis, but I'm bad at it. I like bowling. I'm actually pretty good at bowling. So I was surprised when, like, oh, let's go to the firing range. Okay, yeah, I'll shoot once or twice. And then bullseye. All right, let's talk about where these errors come from in a more reasonable setting in the laboratory as opposed to the firing range. So, when you are working with tools, there is a very specific procedure that you want to follow. And if you don't follow that procedure and you aren't aware that you aren't following that, you can get error that creeps in. So the first example that I'm going to show you is parallax error. I'm going to show you a video of somebody looking at a balance. And I need to hit pause here so that I can get the video on the screen before he takes off running with the example here. Now, this is going to be kind of blurry, unfortunately. So I'm going to try and make this... Am I clicked on the right thing? Yeah, there we go. Oops, hold on. I clicked on the wrong thing. Never mind. There we go. So I'm going to do that, and then I will just make this really big. There we go. All right. So the needle is in the middle here, and this will autofocus, but you're going to see that depending on where you stand and look at the balance, you get a different result. So here we go.
I'm going to zoom in here. I'm going to say this looks to me like the answer is about 2.41 grams. Now, if I were on the other side here, and I looked at it, I'd say, no, you know what? That looks a little bit more like maybe 2.66 grams. And neither one of us is correct. The best way to circumvent parallax errors is to look at something front and center, which is fairly obvious, but sometimes you forget it. So let's just think about this here. If I look at it from the straight and center, what I find is that looks like it's about maybe 2.56 grams.
So as you can see, depending on where you stand, you get a different result. Now, duh, why would you stand left or right in front of a balance, right? But most of the time, we're going to be working with glassware, and the glassware is going to be aligned vertically. So if I go back to this... oops, I clicked on the wrong thing. If I go back to this picture here, If I have something in front of me, you want it to be level, but that object may be on the bench, and that may be well below your eyesight, so you'd have to stoop down to look at it. Or it might be on a clamp that is above you, and you'd have to adjust that or stand on something that is like an elevation apparatus or a stepladder. I like to call it the elevation apparatus. And obviously that takes effort. So sometimes people might just like look at something quickly and be like, oh, that's what it looks like. When in reality, you're looking at it from a weird angle above or below and you get the wrong answer. So it may not be as obvious in some applications. This type of error is called systematic error. A systematic error is an error in procedure. And what that means is that you are basically doing the experiment wrong. But you may do that mistake over and over and over again and still get good precision. Because if you make the same mistake, that error should carry over into your result and you'll have precise results. This is the example where the person didn't sight in their weapon properly, and then all of their shots deviated to the left slightly. If they're looking down the sight the wrong way, they're not actually looking at the bullseye. The barrel of the weapon is pointed slightly over in a different direction. And so as a result, you get the same error over and over and over. It all goes to the left. There are many different ways that you can do systematic errors in measurement. The most common one, what we just showed you, is parallax. Other common errors would be omitting a step. So if you go to the balance and you don't hit tare, then the number doesn't zero out, and then you would be including the weight of whatever container you're using, and all of your numbers would be too big or too small, depending on what application you're doing. So for systematic errors, whenever you have a systematic error, you're always going to have the same problem in your result. And an interesting consequence of that is that when you take the average of all your data, taking the average does not reduce your systematic error. Because if you take the average of X error over every trial, the average of X times 4 divided by 4 is still X, right? So if you're off in the same direction every trial and you average it, that's going to carry over into your average. Now, there are other types of error, and we have varying sources for those types of error that are very difficult to pinpoint or define. And so we call these random errors. A random error would be something like, I interpret the answer as 46.2, but you interpret it as 46.4. I wrote down the first data point, and you wrote down the second data point. And then we use that combination of data together. If we kept alternating who writes down data points like that, randomly some will be too high and some will be too low because we're basing this off perception. Other things that could affect this are just like conditions outside of the experiment. So like if you're in a room where you're measuring something where temperature is important to the experiment and the heater keeps turning on and off as the temperature in the room goes up and down and fluctuates, that will affect your results in a random manner depending on when you collect your data. Now, if the error is truly random, then if this is the true value, some of your data is going to be on the too high side, and some of your data will be on the too low side. And when you take the average, the ones that are too high will average out with the ones that are too low, and you get a result that's still close to the center. So random error can be averaged out. In other words, this is the basis for why you take multiple measurements. If you have only 2 data points, there's the true value, and these are the data points that you collect, you might think, oh, they're pretty close together. Then you take a third data point and a fourth data point, and the more that you take, the closer you will get to the correct answer. Now, random error will affect precision. Precision can also affect accuracy if your precision is too low. Generally speaking, though, if you're doing the experiment correctly, random error will exist. You're never going to get the same answer every time, but you can at least reduce it down to an acceptable answer and then have faith that the result that you have collected is correct. All right. There's the discussion on averaging, which we just talked about. All right, and there's our picture. So when you are in the laboratory, the one that I care about most, believe it or not, is this one. So if we were actually in a lab, I'm not really going to test you on accuracy. What I'm going to be testing you on is precision. And what that means is that if you can do the procedure correctly and get the same result every time, then you're going to be precise. Now, if you're doing the procedure correctly and getting all your points very close together, presumably the accuracy should follow. But this is the one that's really the measure of skill. And you could have a really good lab technique and then just make one error somewhere and your answer could be totally off. And if you get 9 parts out of 10 correct, obviously I should give you some credit for those 9 parts, right? So I personally value, in a level 1 chemistry class like this is introductory, I value precision more than accuracy. Now, I'm just mentioning that because it's in the slides. In this class that we're going to be taking, you're not going to be actually doing any laboratory work, but do keep this in mind in the fall or in the winter of the coming quarters, that when we do go back to the laboratory and we can actually start doing experiments, that try to be as precise as you can. If all of your data falls together, that's good. If your data seems to be all over the place, do more trials if you have time. All right, let me just take a sip of water here real quick. All right. So now that we know what we're up against when we are getting measurements out of tools and ways that this could go wrong, let's talk about the results that come out of us using said tools. So for this example, I'm going to use a ruler. If you have a ruler that only has lines every centimeter, that is not going to be as good as a ruler that has lines in every millimeter. And the reason for this is because millimeters are smaller than centimeters, so there's going to be less error with the millimeter ruler. You get a better idea of the object's length. How do we represent that in a number that I can give to another person and say, this is the length of this object? Let's look at an example of this on an actual ruler on a screen here. So what I'm going to do is, I unfortunately can't zoom this in with my version of PowerPoint, so we'll do the best that we can here. But with this object that is on the screen, I want you to type in the chat what you think the length of this is if the object is flush with the start of the ruler at 0 and the units are centimeters. So type your number in the chat. Don't forget to include your units. Trying to make it bigger here for you because we're going to actually draw on this page anyway. All right, so we got some numbers coming in. So what I'm going to show you is the procedure for how to measure anything using a tool. Yeah, I can snip all sorts of things. I can make things bigger. I can do all sorts of stuff with this. Like, this is why I like streaming with OBS as opposed to using Zoom, because you cannot do this with Zoom. Like, Zoom is extremely frustrating, and it captures your screen and that's it. I need more flexibility than that. All right. Let me make this a little bigger here. All right. How do we measure anything? Measuring anything is very straightforward, but we have to follow these directions very precisely. So here we go. Step 1. Find the 2 marks the object falls between. So I'm going to go to my ruler, and I'm in a different window now, so I got to get a different pen. And I want this to be in a color that we can see. Okay. So I'm looking at my ruler now. And you should be able to see the little dot there. And so here's my object. It falls right here. So this is the mark, and this is the mark that my object falls between. And I'm going to write down their values as shown. So this is 11.1, 2, 3, 4, 5, 6. So this one's 11.6. This one's 11.7. So I know that my object is between 11.6 and 11.7 centimeters long. All right, that's step 1. Step 2, write the value of the smaller mark. Okay, what is smaller, 11.6 or 11.7? Well, obviously 11.6 is, so we're going to write that down. And then finally, step 3, we're going to estimate the next 1 digit. And the reason that we're going to estimate the next 1 digit is because we have some information as to what this digit is. For example, if this object falls right here, is the next digit 0? And obviously the answer to that is no, it would have fallen right on the line if it did. So 0 cannot be the next digit. Is the next digit 9? Well, no, that would have fallen well over here, right next to this other line, right? So that can't be it either. What numbers are acceptable to write down for this digit, based on the fact that it seems to have fallen pretty close to the center? What would you write down for the measurement of this object? And you've already done that. Everybody said 11.65, because it's kind of in the middle, right? And that would be an acceptable measurement. You could also write down 11. Oops, you can't see that because I've gone off of what I've cropped here. You could also write down 11.64 or 11.66. These are also acceptable because, again, interpretation and human perception is somewhat arbitrary, right? Maybe it looks a little bit more to the left on your screen because your screen is rendering in a low resolution right now. Maybe it looks like it's a little bit to the right for the same reason. Maybe you can't tell because it's really tiny. And I don't know how big I can make this. Okay, did that help? Probably not, right? So there is a range of acceptable answers, and there's a range of unacceptable answers. And so we would say that all of these are fine. Now here's something that we can't do. Notice how I said to estimate the next 1 digit. Why can't I do something like this? Why can't I just add another number down there? And the answer to that question is, can you tell the difference between 0.052 and 0.050 on this scale? For the scale that we're looking at, we'd just be guessing randomly, right? Like, I have no real basis for whether that last digit would be 2 or 0 or 9 or 7 or 4 or what. I can't tell because I don't have any lines to guide me. I'm essentially guessing. Any digit where you would have to essentially guess completely arbitrarily, we should not include because we don't know what it is. It could be any number. But this number right here, this 5, we know with some degree of precision that it's either 5 or real close to 5. So whenever you make your measurements, follow these rules. Find out what the marks are, write the value of the smaller mark, and then estimate the next one digit. Okay? Don't estimate more than that because the second digit you'd be guessing. You also do not want to just arbitrarily write 0 for an extra digit. Guess the next one digit. Or, I'm sorry, estimate the next one digit. You are allowed to estimate 0 as the next digit. If you land right on a line and you think, I think that's 11.60, you're totally allowed to do that, okay? So don't omit the 0 because 0 has no value. Because in this application, it does have a value. We know the measurement would be 0 if 0 is the next one digit. All right, so that's how you measure anything. And you're going to apply that strategy for any device that has markings on it that you need to acquire a number for. This is what I got, but I also am able to zoom in the screen really well when I am writing the slide. So 11.64 is acceptable, 11.65 is acceptable, etc. I've already done the measurement rules here, so here they are. Oops. I only wrote 2 rules because I condensed the first 2 into one step here. But that's fine. The whole point of the estimated next one digit that we have here is so that the last digit that you're writing is close enough to the true value that it's worthwhile to write it. So as practice, and we're running out of time here, so I'm going to have you do this example before we call it a day. I'm going to give you block A and block B. And what I want you to do is write the appropriate measurement for block A and block B. But they're kind of small, so what I'm going to do is first I need to move this to the top here. Where's window capture? There it is. I need to move this up. Okay. So now it's at the top. So when I do this to it, it should go over the chat. Unfortunately, I can't make it any wider than that. There we go. All right. So give me a measurement for ruler A and ruler B. And then we'll go over the answers in just a second. We'll call it a day. Alright, so I'm going to make this smaller again. If I can click on it. I'm like right at the edge of the screen. There we go. It'll let me click on it there. Ooh, I made it upside down. That's not what I want. Woo, upside down. That's a little too small now. Alright, so now what I'm going to do is I'm in the wrong screen here. There we go. So I'm going to write down the 2 marks for ruler A. Oh, wrong color. Hold on. And so those marks are 4 and 5. So that was step 1. Step 2, write the value of the smaller mark. So I'm going to write 4. And then I'm going to guess the next digit. So it's right here, right in the middle. I think that's a great measurement to make for this. And everybody wrote that. So that's good. We're all very consistent there. Now there's a little deviation over here because the marks are now much closer together. But everybody had the right idea. So I would write, okay, this is 4.5 for that smaller mark. And then I'm sort of between them. So I'm going to guess the next digit to be 5. And so you can see that when you get more marks, you get to write down more digits. If I had 10 marks between each of these marks, I could then get the next digit after that. And that's where we start to get into the realm of, oh, I need a machine to do this, because a machine can put a bunch of marks between really tiny things and discern that much better than our eyes can. So good job on getting the right answers there. All right, last thing that we'll talk about real quick is that if you have a digital device that is giving you numbers, the estimated digit is the last number. So like if I have a balance that writes down these numbers here, this is the last number that the system is trying to approximate. And so what that would mean is that if a balance was showing you that number, if I could make the balance like one of these like needle things where here's my little doodad or whatever, then here would be the line for 0.25, and here would be the line for 0.26, and this is just right on the end there. So the balance would report this number as the result. Now, if you do this and it starts fluctuating, because balances tilt up and down, right? So this might go up and down. A mechanical balance will do this, and so will an analytical balance, the one that just prints out the number on a display for you. It'll wobble a little bit because of gravity and stuff until it settles. What number should you report? Well, you just take the average of these. So if you ever have a balance that seems to fluctuate, it goes up and down and up and down, write down the number that is the average of what you see, and put that in your notebook. Don't stand at a balance for 20 minutes waiting for it to calibrate or equilibrate, because that's just wasting your time for a number that really doesn't matter. And you're taking multiple trials anyway, so that result will get averaged out. All right, there is a practice slide here that you can do on your own time here. I'm going to skip that. We're going to start tomorrow on the next section, which is significant figures, where we learn all about how we've done addition and subtraction for all of our lives wrong, which is not a good feeling probably, but we'll save that for next week, so you can just dread that over the weekend. In week 2, quiz number 1 will go up once we finish chapter 2. The lab assignment for lab number 1 is currently posted. I will go put a due date on that after this lecture is done and posted to YouTube and put it in the playlist. And there will be new music for week 2. We're done with Donkey Kong Country. I don't know what will be up there, whatever I'm feeling like. But for now, that's all we've got. Have a wonderful weekend, and welcome to Chem 140. We will see you for what's coming up in week 2.